Right.
Good morning and welcome to the ALCF Mini Core Developer Sessions for October 2018. My name is Yasaman Qadar and I am a member of the ALCF Performance Engineering team assisting with the training. This webinar series was created to foster discussion between the developers of the emerging Mini Core hardware and software and the early users of that technology. Today's topic is preparing an application for hybrid supercomputing using Cray's tool suite. And we are pleased to have with us John Levesque. John is responsible for the group performing application porting and optimization for breakthrough science projects. Levesque has been in high-performance computing for over 40 years. He is also a member of Cray's Chief Technology Office, heading the company's efforts in application performance. Now I'll turn it over to John. John, please go ahead.
Hi. Great to talk to you today. And it turns out I've been in high-performance computing for 52 years. So that's an old, I should have updated that. But today I'm going to talk about taking an all-MPI application and moving it to a hybrid code using MPI and OpenMP. So the outline will be to first investigate the all-MPI application. Now, Cray has some very good profiling tools. The two that we're going to be using initially here are Perftools-lite and Perftools-lite-loops. Those tools are going to allow us to identify potential high-level loops to parallelize. Then we're going to use the Reveal product, which does scoping analysis for loops. So it will look at a loop, and that loop can contain subroutine and function calls, and it will try to identify all those variables that are shared and those that should be private. And then we're going to introduce OpenMP directives. Along the way, we will be doing timings, comparing our OpenMP code to the original code. The next step will be to look at memory usage. The tool we will use for that is called Perftools-lite-hbm. And then finally, once we have a really good OpenMP code, hybrid code, we're going to move it to OpenMP for accelerators, because this is something that I think will be very helpful for developers, that once you have a really good OpenMP code, it's much easier to move to accelerators. Now, the first thing we're going to do is use Perftools-lite. And to do this, all you have to do is module load Perftools-lite. Later, we will use Perftools-lite-loops. Now, these modules require that Perftools, that should be Perftools base, should already be loaded. And that is usually the default on Crays, so all you have to do is load Perftools-lite. Then you build the application, you run the application, and the statistics report comes out within standard out. Now, the older Perftools Cray tools required you to do a pat build and a pat report, and that is not needed when you use Perftools-lite. After the run, not only do you get a report, but you also get a directory of profile data so that you can examine it using different options using pat report. So The application we're looking at is Leslie 3D. I really like Leslie 3D. It's not real complicated, but it has some really good examples of how you can optimize code. Now, this is one of the 9 tables that comes out when you run Perftools-lite. And what we have here is Perftools-lite does sampling every 100th of a second. And so the first column, you have the percent of time used by the subroutine. Now, these are inclusive time. I'm sorry, these are exclusive times. Boy, I made a couple errors there. And the note on the table says the right time. So this is the time excluding routines that are called from it within the routine. I'll fix this before I send it out to you. One other very interesting thing is this also gives you imbalance. In other words, one thing that really hurts you a lot when you're threading is when you have imbalance between the workers. Now, this imbalance is not too bad. It's really down in the 1 to 2%. And as you can see, MPI is very low. Now, one thing on this table, nothing below 1% is listed. Now, I can get everything, and I'll mention that a little later. Now, this was a run using 8 nodes and a single MPI task on each node, and this was using Broadwell. So we're really only using 1 core on each of the nodes. And in order to really investigate OpenMP, this is the way to start, is by just looking where you're using 1 MPI task on a node. All right, now, if I had loaded Perftools-lite-loops instead of Perftools-lite, I would get a table that shows loops in the application. And this is extremely important for threading because it's important that you know how much computation is in the loop, but also what the loop lengths are, the iteration count. And so basically what you see is the top level loop is 99.4% of the code. Now it turns out this is the timestep loop, and we're not going to parallelize that. The second highest loop is a loop that only goes 1 to 2, and this is kind of 2 separate sweeps of the grid. So we're not going to parallelize that as well. But then we see down into flux, K, J, and I have highlighted 3 loops that I say are the most important loops. Now, how did I know that those were the most important loops? Well, after I run the Perftools-lite run, I can do a pat report asking for the call tree and give it the directory produced by Perftools-lite-loops. Now, this produces a call tree with do loops included, which is phenomenal. So what you see is we start with the main routine, less 3D, and there is that time step loop, less 3D loop 216, and then the loop that goes 2 iterations. But then notice in flux K, the high-level loop in flux K on loop 28. And it turns out there is also a second loop, 29, nested within that outer loop. Now that loop calls this CK. Now the reason I can tell this is because of the indentation. And the number over on the left-hand margin tells you the depth in the call tree. And so what we see is that 20% of the time spent in flux K comes from that loop. And then we have a 6.4% coming from flux K exclusive of anything it calls, and extra PK is called from there. So flux K is a pretty important loop. It's using almost a third of the time. And notice that flux I has a similar structure, and flux J has a similar structure. And then finally we have parallel. That actually is where the MPI is called. And now let's see, just to make sure I cover everything here, that second column is Perftools-lite-loops does not do sampling. It does tracing. So rather than getting samples, you are getting times in seconds. And then the number of calls is in the third column, and then the actual entry is in the last column. So I absolutely love this report. This is, I think, the most important report when you start analyzing a code to thread on KNL or on any of the Xeons, and as we can see when you move to accelerators. Okay, now, so that information, we're going to take that information and we're going to feed it into Reveal. Now, in order to use Reveal, you have to generate a program library. And this enables Reveal to do whole program analysis, which is basically able to scope loops that contain subroutines and functions. So when you do your compile, the first option is to get an annotated listing. The second option is WP, which stands for whole program. And the third option is to tell it to generate a program library file called Leslie 3D-PL. Then, after I do that, I then enter the command reveal Leslie 3D-PL, which is that program library, and then I give it the Perftools-lite-loops data directory that was generated when you made the run with Perftools-lite-loops. Any questions so far? I feel like I'm going pretty fast. I tried to put in all the commands that you needed to use so that you should be able to just pick this up and use it. The one thing, you cannot have Perftools-lite and Perftools-lite-loops loaded at the same time. So when you move from Perftools-lite to Perftools-lite-loops, you have to swap those, do a module swap. All right, so up pops Reveal. You do have to have X windows loaded like on your laptop. And so what Reveal does is it highlights the loop in the program that uses the most time that doesn't have an obvious inhibitor. An obvious inhibitor is something like I/O and I/O primarily. And so it's highlighting flux K at line 28. Now over in the other window, we see that on line 28, there's a do J equal 1 to JC max from the, I should have mentioned it, from the Perftools-lite-loops display, that was 90. So in fact, both the J and the K loops are 90. Now down below, you actually have information on what the compiler did with the loop. It says that the loop starting at line 28 has been flattened, which is basically not a weight loss program, but it inlines all the calls. Now on the side, the capital F means flattened. The capital V means that that was vectorized. The D means that that is not executed. It's deleted because in scheme is not equal to 2. And then F, the little f down on line 46, says that those 3 lines are fused with the line, with the array syntax on line 31. So all of those array syntaxes are fused into one loop. Okay, so that's kind of really interesting. But what I'm going to do now is I am going to right-click on the flux K at 28, and a drop-down menu will come up, and I'm going to say Scope. And so when I say Scope, this window comes up. And basically, it comes up with the source file that I'm looking at and the do loop that I want to scope. Now, right now, in fact, Reveal went kind of overboard against my advice. And they have this thing where you can do everything automatically. And that's what that lightning bolt is. In other words, that lightning bolt basically means click that and you're going to get hurt. No, it's going to parallelize everything it can. But I find that that is way too confusing. And so what I prefer to do is just to look at the important loops by myself without, automatic, and try to determine what to do next. And this is extremely helpful. Now this encompasses, I would say, probably on the order of maybe 300 or 400 lines of code. And what Reveal is doing is everything it knows for sure that is private, it scopes private. Everything it knows for sure is shared, it scopes shared. And those things that it doesn't know what to do with, it says unresolved. Now, it is up to the user to investigate the usage of these and determine if those unresolved scopes are private or shared. And so I'll show you how to do that. First thing we're going to do is click on FSK, and in the window, it's going to highlight all the uses of FSK. Now it's kind of interesting. Notice that FSK is set, and then use. Now, FSK is not dependent upon J. J is the loop we're parallelizing on, remember. And so what we call this is an array constant. In other words, an array is set by each thread and then used later. Now, for the data dependency analysis to work here, all of the elements of FSK that are used must be set. And the problem the compiler's running into is you notice that there's some FSKs that are set and they're set with the third subscript, either a number, and then down below it has a loop that goes from 1 to 5, and it can't convince itself that everything that you use is being set, so it's afraid of a loop carried dependency. Now, it's the same thing with QS. And the compiler just tends to be more conservative than it should be, which in the long run, I think is a good thing. Now, what we can do then, and what we did, is we went through and we determined that FSK is private. So what I did is I clicked on the unresolved, and a drop-down menu appeared, and I selected private. FSK with the red eye means that came from an inlined routine. And that is also private. Actually, it's the same array. And then L was private, and QS is private. And so all the ones that I changed the scope on, they retain that info just to make sure that you know which ones you changed going forward. All right, so the next thing I'm going to do is down in the bottom left corner, it says Insert Directives. So I'm going to do that. And voila, the directives are inserted into the source code. And notice that you get a directive saying that they're inserted by Cray reveal, and it does always default none. So it's going to scope all the private and the shared, just to be cautious. Okay, so we did one of the loops. And now the other three, in matter of fact, there are 3, 6, there are like 8 loops that I did along these lines. There wasn't anything different about those other loops. And then when we actually inserted that by reveal and compiled it with the H list equal A, notice that the M stands for multitasking. Little m says that this loop was multitask. The F is flattened, and the V is vector. Okay. So, and this is the bottom of that loop. Now, there was one case update which used 13%, which was, only like, or 13 seconds, which was only about 13 or 3%. It actually did this automatically. So when you scope it, it comes up and it says, hey, I was able to scope everything. And so now, after doing those 8 loops, I actually ran it with 1 MPI task in 44 threads. And so what you see is it went from 296 seconds, now this is sampling again, down to 11 seconds. And you can see that the flux really went down quite a bit. The fluxes, the update, and so most of these really were reduced quite a bit. And now MPI is a much larger percent because the computation was reduced. Now, the problem with this is not fair because the profile on the left is only using 1 core. The profile on the right is using 44 cores. So let's run MPI on all the cores. So we're running 8 nodes with 44 MPI tasks per node. And compare that to 8 nodes with 1 MPI task per node and 44 threads. Now, we still beat all-MPI. However, look at the performance of the flux loop. So MPI is actually running like a factor of 2 faster if we don't do threading. Now, why is that? Well, it's because these machines are NUMA machines, non-uniform memory access. Now, the OpenMP run, I ran 44 threads on a Broadwell, 2 sockets, where each socket had 22 cores. The MPI run, I ran on 2 sockets, and I made sure that 22 MPI tasks were on each socket. All right. Now, there is on the Perftools-lite, on one of the other tables, table 3, there is something new, and this is extremely valuable. What it's showing you is that there are 2 NUMA regions on this Broadwell socket. NUMA node 0 is socket 1 or 0, and NUMA node 1 is the second socket. Now notice the local memory traffic in NUMA node 0. It's actually, and this is in gigabytes. Remote memory traffic is the traffic getting data from the other socket. So what this is saying is the threads on socket, the first socket, are actually getting most of its data from the first socket. But the threads on the second socket, which are down the second section, are getting most of its data from the second socket, but there is a large percent coming from the first socket. Or excuse me, I said that. The remote memory traffic is to the other socket. So the threads that are on the second socket are getting most of its data from the other socket, which means that, in fact, look at the memory traffic gigabytes per second. It's much lower on the threads on the second socket. And the percent of peak is, while it's 20% on the threads on the first socket, It's only 8% on the second socket. So what this is saying is that half of your threads are really running slower because the memory it needs, it has to go across the, I think it's called QPI, to get stuff on the other socket. Now let's look at the MPI table. MPI forces locality, and you can see this from this report. So notice that the it is actually the local memory traffic is very high, whether you're on NUMA node 0 or NUMA node 1. And the remote memory traffic is very low.
I'm a little confused from table 2. It seems that the threads perform better, but it sounds like MPI performed better. Did MPI perform better? Where did we see it?
Okay, so MPI performs better. Notice the table on the left, notice that flux J, flux I, flux K is running faster than the flux KJI on the right. And so MPI, the computation, look at the user time for MPI. Okay, so the user time is less for MPI. And what we're trying to figure out is why. Why is the user time less for MPI? And so and what we have determined is it's because of this NUMA traffic. So let's do the following. Let's run 2 MPI tasks on each node and 22 threads. So this is a hybrid code. We have both MPI and OpenMP. We can easily say, I want to run 2 MPI tasks, 1 on each socket, and each MPI task will have 22 threads. Now, while the MPI still runs, the user is still a little faster. Now, the hybrid code is really very good. Is that clear now? Why we did this exercise?
Yes.
Okay.
Yes.
Good. Thank you for asking that question, because I can see how that can get lost. All right, now, so we're vectorizing and we're parallelizing very well. I mean, we're getting a significant speed up here. There is one thing that we haven't done that we need to do, and that is to look at memory bandwidth. So this is a new tool, and we load Perftools-lite-hbm. HBM stands for high bandwidth memory. We actually developed this for K&L, and then found out it's extremely useful for looking at cache utilization on any machine. Now, what we're seeing here is a list of, and this is sampling, they are showing us on the line level what lines in the program are getting the most faults in the last level cache. In other words, those numbers that are given there are telling you how many times the CPU asked for a variable and it wasn't in the last level cache. Now, The stalls are actually stalls, but those stalls, we cannot tell if it's due to waiting for memory or waiting for the functional unit. We assume that most of it is waiting for memory because this is really somewhat memory bandwidth limited. Now, the great thing about this is we have the line number in flux J, or the line numbers in flux J, that account for 23% of the cache misses in the whole program. So let's look at it. Now, I have been writing Fortran code for 50 years. I absolutely hate array syntax. I absolutely hate it. It really forces the compiler to do things differently. Now, I agree that this is saying that that was fused with that down there. That's what that little f is. But still, what this is pointing out is that that line 36 that's coming from here is where there's array syntax. And line 74 and 81 is where there's array syntax. All right? So let's get rid of the array syntax. All right. So I removed the array syntax within the entire code. And it actually runs, 5% faster. Now, if I were running a larger problem, that difference would be larger. But that's okay. I mean, I don't like array syntax. I don't think you should be using array syntax because the compilers are much better at optimizing the code if it's a nice do loop. Okay, so next step. Yes?
Does array syntax help compiler to vectorize the code?
Well, it forces it to, but the compilers can really vectorize do loops very well. So it doesn't really help that much. Okay, so let's talk about
following up on that question. So it sounds like you would advocate for using OMP SIMD directives and things along those natures rather than using array syntax to force vectorization. Is that correct?
Yes, absolutely. Absolutely. Now, in this industry, all of us do not agree. And some people are going to say, hey, array syntax is so much productive. But I believe getting productivity and throwing away even 5% performance is a bad thing. Now, this is what I find to be absolutely amazing. All right, first we're going to go to OpenACC. Now, I must admit that not all the compilers are going to be able to do this. I'm using the Cray compiler, all right? Now, I'm looking at one of those loops, and what I did is I say, okay, I'm going to put in OpenACC, and that's all I have to do to get this loop to run on the accelerator. All I have to do is put that one directive on there. And all I have to do is scope private. I don't want to deal with shares. So that one directive, and notice it's the same private as under the if I'm running OpenMP. Now, this is the great thing about the Cray compiler. This will run on the accelerator and get the right answers. And the reason for that is, first, it gives you this listing where the G says this goes on the GPU. The little g says I am on. There are actually two parallel loops there that it's doing. One is the G on the outside across the SMs and the G on the inside. Now, a point here. This is where I remove the array syntax. Now, this is much better on the accelerator as well. Now, but at the end of the listing, it tells you that the region starting on line 22 and ending on line 88 was placed on the accelerator. Now, in order to get that to work, it is going to copy all of these arrays over there, and then some of them will be copy out or copy. Copy is in and out, and copy in is just in. So, this is going to run on the accelerator. It's not going to run very fast because of the overhead for moving the data. So what we then do is, we turn all of our OpenMP high-level loops into OpenACC. Now we look at the data that is being moved over and moved back, and we want to identify a place in the call tree where we can move that data to the accelerator. All right? And we can also use Perftools, there's another mistake, to investigate accelerator performance. Now, there is a Perftools-lite GPU, but it doesn't work very good. So I use Perftools, and if you use Perftools, you have to do the pat build, run the executable, and then a pat report. Now, they will fix Perftools-lite GPU, and you'll probably, next year, it'll be a lot better. Okay, so where do we want to introduce the data region? We go back to the call tree, and we say, hey, if we can introduce the data region outside the timestep loop, that's going to really reduce the amount of data transfer that we need to do. Okay, so we go to the main routine, and so I put in a data copy, and I copy all those arrays. Now, this will also do a copy out of all those arrays after the do while. But when I do that, I introduce a lot more work, because now I have to either put all of the work within the data region on the accelerator or transfer data back and forth to the host before and after that work. And I'll show you a couple examples. All right, so here is a loop that was in the main routine. And so what we did on this is I figured, well, since we are putting it on the accelerator, we might as well also do shared memory parallelization on it. And so we do that. And then on the right, this is where we call parallel. And so what I have to do is update the host with Q and HF, and then update the device after that with Q, U, V, and W. Now, you can't tell that by what's being passed to parallel. you have to go into parallel and see what arrays it's working on. So there is work to do there that is introduced because I put that data region so high up the call chain. All right, now here's the perf tools of fixing all this. I only could run this on 4 nodes because I only had 4 GPUs on the machine I was using. But this is very interesting. What it's telling me is that those copies in and out in the main program are using 46% of the total time. And these ACC sync waits are all of those OpenMP loops or OpenACC loops that are in fact being used there. No, I'm sorry, I said something wrong. The copy at 353 and 343 are the copies I need for the parallel, for the halo exchange. The copies on 30 and 29 are the copies for before I enter the time step loop, and then the ones down below is after. But those sync waits are all waiting for the accelerator to execute the kernel. And if you look at this, this is running much faster than the host, the OpenMP on the host. And I only ran it on 4 GPUs. Now, 2 more slides. So I'm worried about OpenACC. Newer accelerator installations like, just announced NERSC and Livermore are really moving to OpenMP directives for accelerators. And as these OpenMP compilers become more robust, I think OpenACC could become extinct. There is a lot of usage of OpenACC, but I think eventually, because I'm going to show you it's pretty easy to convert from OpenACC to OpenMP. And so this is what I had to do to actually convert it to OpenMP 4.5. Now I took out the if-def. Now one thing that you have to do with OpenMP 4.5 is if you call a subroutine from within a kernel, you have to declare it in a target statement. That's what line 13 is. Then you have to do the data map of all the variables that you're using. Now, the compiler is going to know which ones are up to date on the accelerator. It is not going to do transfers of all those. But you can see, really, I have the data region, which is now called target data map. I have the target teams distribute, which is like the parallel loop. So this is doing exactly the same thing as the OpenACC did. Now, if I go to the main program, I use the data map to from. And so the compiler is going to know when it has to move that data and when it doesn't. So you're just kind of specifying what data you really need over on the GPU, and you also need it back on the host. Now, when we get down to the boundary exchange, we do this target update from the device. And that bottom one should be 2. That's a mistake. I wonder why I got the right answer. But anyway, that bottom one should be target update to the device instead of from. But I ran it and it worked. All right. So this is not the most efficient way to leave this. We, in parallel, that parallel is doing packing and unpacking of the halos on the host. We need to go into parallel and put the packing and unpacking of the halos on the accelerators and use GPU Direct to transfer the halos between accelerators. And I know I have presentations on the web that does this for S3D. But if you have any questions about that, I can get you examples. Now, a cool thing that Cray has is that if you're going to run this code on the accelerator, you load that module. If you run it threaded on the host, you load that module. So you can have exactly the same code, and you can either run it on the host using OpenMP or on the accelerator using OpenMP. And that's it.
I would like to thank John for his presentation, and thank you all for attending the installment of ALCF mini core developer sessions. We hope to get your direct feedback or on how to improve it or on requests for your future topics. You're welcome to send an email directly to the devsessions@alcf.al.gov